there's obviously a lot of interest in this area, and I suggest that we focus on it during breaks or later. Anyway, thank you very much for your very good talk.
Thank you very much for inviting.
Our next talk is by Steve Augustino and John Blitz on quantum chemical application of DRIFTS and DRIFTS to the characterization of vinyl acetate catalyst surfaces. Steve will be giving the talk.
Well, it seems like just about anybody who's ever worked on a heterogeneous catalyst has wondered at some time or another, what does that active phase look like? And so, what we generally do as catalyst chemists is we either shine light on that catalyst, or we bounce electrons off that catalyst, or we hit it with an ion or two. And that gives us a pretty good picture, a physical picture of what that surface looks like. But if you have that common problem, which a lot of us do, in that your surface, the percentage of your surface that actually participates in that reaction is rather small, you always have that nagging question in the back of your mind: is this picture really of the active site, or does it have anything to do with the active site at all? So what people are now doing is they're putting reaction stages on their UHV chambers or on their microscopes, or they're actually coupling analytical techniques to actual catalytic reactions to get a picture of a reaction history of the catalyst as it corresponds to that catalyst activity. So that's kind of the same type of thing that John and I were trying to do when we coupled the DRIFTS, which is, again, as Professor Slocum said, diffuse reflectance, infrared, Fourier transforms, and spectrometer with the mass spec. Now, again, I won't talk much about DRIFTS, just to, again, say that it's a infrared technique, because it's the same information as transmission infrared, but it's more surface sensitive. And basically, we put this contraption together to take a look at a vinyl acetate catalyst surface as we do some transient analysis. We're doing some temperature program reactions, looking how that surface changes with reaction conditions. I want to take a quick look at the chemistry with you. Basically, we can write vinyl acetate, the vinyl acetate reaction very simply, in so much as we combine ethylene and acetic acid in the presence of oxygen, and we come out with vinyl acetate and water. We generally do it with a supported palladium or palladium alloy catalyst, and we promote that catalyst with potassium. The salt that we like to use is potassium acetate. Now, looking at that system, you can see that there's a lot of infrared active components. And that was our first indication this would be a good system to look at with DRIFTS. I want to take a brief excursion into some kinetics, and this is by no means a exhaustive look at the kinetics that have been done in the system, but it's a look at a couple of studies that agree very well with each other, and it kind of sets up my problem, so that's why I wanted to deal with these a little bit. But basically, two groups, Nakamura and Yusui and Samanos, Buki, and Montano, have looked at this system, and it's been, I guess, over 20 years now. Basically, they've seen that ethylene was first order. They have both seen that oxygen is half order kinetics, but it's interesting that they see similar results with acetic acid. But one interprets it as being a partial order reaction, following some type of Langmuir-Hinchlwood dependence, while the other interprets that as being zero order. So that's what we're focusing on right now, is what is acetic acid doing in this reaction? Why, if we see similar results, do we have different interpretations? Show you some kinetic results that we've gotten that again agree with those previous two studies. Basically, we look at the reaction rate of vinyl acetate formation as a function of acetic acid pressure. And this is done at atmospheric pressure. We got an ethylene to oxygen ratio of about 9. We change the acetic pressure by changing temperature of a variable temperature sparger, and then make up the excess with helium. But basically, we see that as we increase pressure over this range, we see what we would typically call a Langmuir-Hinchlwood type dependence. That as we go closer and closer to low acetic pressures, we get dependence that get closer and closer to 1. And in fact, this curve is fit with the Langmuir-Hinchlwood approximation, so it does fit fairly well. The problem comes in it is if we can blow up or look very closely at this range, that we would expect, according to Langmuir-Hinchley, that we would have a 0-point intercept. With no acidic pressure, we get no reaction rate. But what we see is that this is essentially flat in this low pressure range, indicating to us already that the surface is saturated with acetic acid at this low pressure. So what does that say? Well, it gives us some type of indication that the positive influence acetic acid has on this rate in this pressure regime is not necessarily due to its interaction as a reagent in the mechanism, but maybe it's interacting with the active site, doing some type of modification of the active site. Now I got more evidence for that, and I'll bring that right up. Basically, we looked at the activation energy of the reaction over the same pressure range. And you see quite clearly that the low pressures, we have an activation energy of about 7.5 kcal. But as we increase the pressure of acetic acid in the reaction, we drop that right off to 5.5 kcal. So again, acetic acid is interacting with that active site in some way, and that's dropping the activation barrier of the reaction. So this is when we started thinking about a DRIFTS mass spec study. And basically this is a setup of our apparatus. What we do is we combine ethylene, oxygen, and acetic acid prior to reaction. We have the ability to switch out nitrogen for any of these reagents at any point in reaction. Run the gas over a controlled atmosphere, variable temperature DRIFTS cell, which serves as our reactor. So we can bounce light off of that surface and get a spectrum. Then we bring that further, bring the effluent out to vent. Before we get there, we tee off into a mass spec. And so basically to describe how we run the experiments, we set up, we pre-treat our catalyst under steady state conditions, then sequentially take out first ethylene, then oxygen and acetic acid, and then we do a temperature program reaction in which we ramp the temperature, but we react ethylene and oxygen with that surface. We get off our product, and as we ramp the temperature, we see the spectrum change. Give you an idea of what we're looking at on the surface. The red trace is a profile we get at steady state. And basically it's assigned all these peaks to just the compounds as they flow through this mass spec independently. But basically what we have here is this group of three is due to ethylene, combination bands and a rotational vibrational band. These three peaks here we have assigned to acetic acid. The two smaller ones are due to the gas phase monomer. This larger band is due to the gas phase dimer and also a surface phase component. What's interesting is as we go through under steady state, we see this band grow in, and what this is palladium acetate. And that, as we run the reaction longer, gets larger and larger. And then this larger band right here is due to our potassium acetate growing phase. Well, what we do is, we take out ethylene, then after a while we take out acetic acid and oxygen, and then we purge with nitrogen, and this is what's left. Basically, we see that we still have a peak here, what we would call the carboxylic region of the spectrum, and I'll just call it, for convenience, a surface carboxylic species. Palladium acetate is still there, as is potassium acetate. So then what we do, we switch it over at room temperature to 10 to 1, or 90 mils per minute ethylene, 10 mils per minute oxygen, and ramp the temperature to about 10 degrees a minute. And you see that if we look at final acetate formation as a function of temperature, we find VA being produced at about 135 degrees C. Now we look at two spectra, one taken before we see VA and one after, and these are offset. So you can see pretty well that it doesn't look like much is going on the surface. But what we do is we can zoom in on this peak right here, our surface carboxylic species, And we see a very small, but I guarantee it's a very reproducible loss of absorption intensity here, indicating that whatever's going on here is interacting with ethylene and oxygen to form vinyl acetate. I want to show you a little broader range of what's going on. This is the same experiment, the same vinyl acetate peak, but now we're looking at all the way up to 300 degrees, and we see at higher temperature form acetic acid. I say 2 batches here. Again, after we form, just after the maximum of the vinyl acetate, we have all the components that we had to start off with. But after we form the first batch of acetic acid at point B here, we see that that occurs with a corresponding attenuation of this peak at 1735 William numbers. And we also lose our palladium acetate peak. Our second batch of acetic acid is made at the expense of our potassium acetate promoting phase. But we were rather intrigued by the fact that we actually see palladium acetate being formed during steady state conditions, so we thought, well, why don't we try to see what palladium acetate will do in our experiment. So basically what we have here is a 5% dispersion of palladium acetate physically mixed with potassium chloride. And again, we're doing the same experiment where we do a temperature program reaction with ethylene and oxygen. Again, we see both vinyl acetate and acetic acid being formed. And this is what's going on the surface. At 120 degrees, there's really not much occurring, and this is our background spectrum. Again, we see the ethylene, and we see now the palladium acetate. At about 130 degrees, it's just right at the foot of this peak. We're just starting to see vinyl acetate come out of that reactor, and you can see, I hope, but maybe you can't, that there's a few squiggles coming in here, right in that acetic acid absorption region. Right at 140 degrees, where we're actually making a sizable amount of vinyl acetate, we're just starting to make acetic acid. These peaks grow in rather pronounced, and you can see them quite well. Again, gas phase, acetic monomer, gas phase dimer, and surface component. At 160 degrees, we're on the downside of vinyl acetate, but the maximum of acetic acid formation. Again, corresponding decrease in these species. And what we find is that we're not making acetic acid primarily due to the oxidation of ethylene, but we're making it through the destruction of our palladium acetate phase. And then at 170 degrees, when it's all over, we just have background squiggles. So let's compare what the surfaces look during the reaction. This is the palladium catalyst promoted with potassium, and again, the components that we saw is the 1735 surface carboxylic species, palladium acetate, potassium acetate. This is taken after we had seen vinyl acetate being formed in the reactor and we quenched the reaction. Again, a broad, not as well defined species, but definitely in the same place. Our palladium acetate, and we see a shoulder coming here that kind of surprised us, but it starts looking like potassium acetate is being formed in the reaction. And if we take it after reaction and blow up the spectrum, you can see quite clearly, again, this species, palladium acetate and potassium acetate promoting phase is being formed. So we start out with a potassium chloride mixture, but through the reaction we actually form the catalyst promoting phase of potassium acetate. So at this point it was real tempting to say, okay, we've got it nailed down. It looks like the catalyst active phase is palladium acetate. We take a palladium catalyst, we do a steady state reaction, we form palladium acetate. We take that, we do a temperature program reaction, we see that without acetic acid present, that can make vinyl acetate. We take palladium acetate and we react it without acetate. We find out that too can make palladium acetate. Seems like the same temperatures. We look at the surfaces, they seem very similar. We even make the same activating phase. But what we wanted to do what we quit was to look at the energetics of the reactions. And to do this, we didn't use the drift cell, but we used a microreactor, again, interfaced to a mass spectrometer. And basically what we wanted to do is look at the kinetics, because the kinetics would give us the activation energy. And the way the reaction was run was that ethylene and oxygen were run in such a great excess that they were essentially constant through the reaction. So we take those concentrations and stick them in our free exponential factor. And we needed to assume that whatever that thing was on the surface, it reacted under first order kinetics to form vinyl acetate. With those assumptions made, you can see we can use a very simple empirical kinetic rate law to define the reaction. Take that derivative with respect to temperature and simplify, and we come out with an equation that we can use to model those temperature probe reactions. Theta here being the temperature ramp rate of our experiment. These are the results. The green is the experimental results, and the red are the fits. And you see for a palladium alumina catalyst that we get a peak again about 135 degrees C, and the fit does rather well. And it gives us an activation energy for that reaction of 37 kcal per mole. If you look at the palladium acetate potassium chloride mixture, we see that the peak is shifted higher temperatures, about 160 degrees C. Again, the fit is satisfactory, and it gives us an activation energy of 93 kcal. We thought at one point that chlorine may be interacting with this, since we take the acetate and exchange it onto the potassium. Where's that chloride going? Maybe it's going back onto the palladium and poisoning. So we took a potassium acetate dispersion of palladium acetate, potassium acetate, and we see that that's probably not the case because we displace that peak even further. Higher temperatures, about 180 degrees, and our activation energy is 129 kcal. So what we see, or what we have postulated at this point, is that the reason that we can make vinyl acetate so much more easily on a supported palladium alumina catalyst is that in this case, there is zero valent palladium or palladium oxide that is actually, I guess you could say ubiquitous. It's adjacent to and underneath the active site. Where here we don't make palladium, zero valent palladium or palladium oxide until late in the reaction. So to summarize our findings, we see that the reaction appears to be promoted by acetic acid, not because of its participation in the reaction as a reagent, but because it lowers the vinyl acetate activation barrier. Now, we see, the reason this is so is because we believe we see the formation of palladium acetate during the reaction. And so taking palladium acetate and modeling, using that as a model, we see that if we run a temperature reaction with no acetic acid, but only ethylene and oxygen, that we can form potassium acetate and what we call surface carboxylic species over these mixtures as we make vinyl acetate. Fourth point is that both the supported catalyst and these mixtures make vinyl acetate, but we see the activation barrier is lower for the supported catalyst. So, in conclusion, we believe that the active phase of vinyl acetate catalyst consists of some form of palladium acetate, but that adjacent palladium oxide or palladium metal is probably very important in the system of the reaction. So I'd like to conclude by expressing my appreciation to Quantum for allowing me to give this talk. Thanks to Vern for putting me in the session.
Do you have any questions?
1700 and 1800 we have a peak. It seems to me that is acetyl group, CH3CO surface group.
Excuse
Is
me?
there any chance acetyl formation?
Mm-hmm.
Is there any included in the mechanism?
I have not included the mechanism. Maybe we can talk about it later. To me, it was the carbonyl group was the natural assignment.
Okay, yeah. But you've been telling that this surface carboxylic group.
Right.
So surface carboxylic groups are all less than 1600, somewhere that range.
I see what you're saying. Okay.
If it is a carbonyl group, that is a CH3C group, we can expect between 1800 and 1700.
Okay. All right. Yeah. I use the term. That's an interesting thing. I use the term carboxylic because again I want to keep that carboxylic group, functional group, intact when I'm reacting with that. That's interesting. I've talked to you about that.
Is there any information where CO2 comes from?
Excuse me?
Where CO2 comes from? It's byproduct.
Well, yeah, CO2 is our deleterious or unwanted byproduct in the reaction. I'm not really prepared to talk about that.
Okay. Thank you very much, Steve. Very interesting talk.